All right. Anyways, so let's talk about Turing machines. So we've talked about so the models of computation we've talked about so far are we've talked about regular languages, and there's certain and regular languages are anything which can be recognized by a deterministic finite automata or a non-deterministic finite automata, or DFA or an NFA. And those are nice because one of the characteristics which defines those is that for a regular language, you have a finite number of states. And this finite number, I know I've mentioned it several times, but it's extremely important that it be finite. You have a finite number of states, and you have a memory that's limited to two things. You have two values you can store in memory. One is the current state you are in, and the other one is where in the word you currently are. Not where in the world is Carmen Sandiego. That's a different memory, requires an encyclopedia, and gets really frustrating when your brother tears out a page that you really needed. How many people have played Where in the World is Carmen Sandiego? How many people know about it from the game show? You guys are a dying breed. It will not be long before I make that joke, and no one will know what I'm talking about.
I had to skip a little bit of the inside.
What?
Just die a little bit on the inside.
It was like when I had my first class and I made a Simpsons reference, and literally no one knew what I was talking about. I'm like, what the hell is wrong with you people? Then I remember my advisor once making one of my professors making a Gunsmoke reference, and I'm like, I know that was a show at one point. And I saw that same look in his eyes that I saw in mine.
It's going to happen to Futurama one day.
What?
It's going to happen to Futurama one day.
Yeah, it'll happen to Futurama someday.
And that'll be...
Yeah, unless it becomes like Shakespeare, and then you can always make Shakespeare references. That's really what I should do. I should just read up on Shakespeare and start making references to like Hamlet and stuff like that in class, because that's contemporary. Classic Aaron being classic. Anyways, so we have regular languages which contain a finite amount of memory, and they contain the memory of two things. We have then context-free languages, and context-free languages can be recognized by a PDA. And the important part of the PDA is that we are remembering the two things that we remembered for regular expressions, but we also have an arbitrarily large amount of memory that we have access to. But we can only access it in a very unique way, which is to say we can only access one element from this we can store an arbitrarily large amount of information, but we can only access one piece of information, and when we access that, we destroy it.
Arbitrarily large stack?
Yes, yeah, an arbitrarily large region of memory. But it happens it's in a stack, but from a more theoretical point of view, the interesting part of this is that, yes, this can be arbitrarily large, but we can only access one element from it at a time, and when we access it, we destroy it. So we have we have an arbitrarily large destructive memory. And that's a fairly constraining, that's nice because there's certain things we can do with the context-free language that we couldn't do with a regular language. In particular, parentheses matching. I know I come back to that, but that's really the best example of what you can do with context-free languages that you can't do with regular languages. So beyond that, we will have Turing machines, and we'll talk about the different types of Turing machines in a minute. But Turing machines don't only just remember the two pieces of information that we had from regular languages, where you are, and what state you're in, but they have an infinitely long tape. And unlike stacks, we can access information without destroying it. On top of that, we can also move back and forth on this. So we don't have to just access the top element of it. We can actually go back, forward, and access anywhere on there. Now, one thing I want to point out is that with the Turing machine, so for these context free languages and regulars, the input sort of existed separately from everything that was going on. For a Turing machine, what will happen is the input will actually be on the tape to begin with. So a Turing machine will have input here, and then at some point you'll have a special character, which is a space, which we typically denote with this weird U-like bracket shape, which, unless you have a Unicode character, you're not going to see. It's a space character, and it's that all the way out for infinity. This symbol cannot appear in the input. The reason for that is as soon as you see this, you know you've reached the end of your input. And so you assume that everything's filled with not that from that point on, so you know where it is. We'll talk in a bit more detail, but before we go into that, this is something that I like to draw an attention to, because if you're thinking about computer science as mathematical, it's really important to be aware of the difference between arbitrarily large and infinitely large. Who has an idea of what the difference between those two is?
Arbitrarily large means as large as you need it to be. Infinitely large means it's already infinite no matter what you need or what you intend to use.
It's very, very close. Infinite is not an actual number. Infinite is merely describing the size of something. So I can have a set that contains an infinite number of elements, and that's perfectly legitimate. Arbitrarily large means it's an actual value, but that there always exists one value that could be bigger than it. So I can have an arbitrarily large amount of data stored in here. But if you say, so is the max, but there's no max on that. So I could have 5,000 elements. My string could be 5,000 elements long. Could I have a string that's 5,001? Yep, I can be bigger than that. This is infinite long. And it's infinite long because you never run out of it. It's a subtle difference between it, but infinite can never be reached. Arbitrarily large can. So I can have an arbitrarily large input string and then process that. That is something which is achievable for me to do. If I say your input can be arbitrarily large, that means you can give me any size input and I will be able to process it. If you told me you have an input string that's infinitely large, I could never finish that because it's always bigger than anything that's possible to finish in a reasonable input time. But there are things which are infinitely large, for example, integers. There are an infinite number of integers. But I would never give you as an input string an infinite number of integers because that's not finite in length. Does that make sense? That distinction becomes very, very, very important once you start getting into upper levels of these elements. Also, other things that become important are degrees of infinity. That we have countable infinite, which are integers. We have uncountable infinite, which are irrational numbers. I guess actually rational and irrational numbers combined. And that's uncountably infinite because we can't enumerate every irrational number out there. And then, oddly enough, we have sets that are bigger than uncountably infinite. We won't have, unfortunately, this is the coolest theoretical part of this class that we have to cut out for time. But there exist sets that are bigger than, that contain more elements than the set of real numbers. I have no idea how to conceptualize this. I can formally define it, but I have no idea how to conceptualize what is something that contains more numbers than the set of real numbers. And there's a whole notation for degrees of infinity, where you use the Hebrew symbol Aleph, and Aleph sub naught is countably infinite. Aleph sub 1 is uncountably infinite real numbers, and then Aleph sub 2 is the thing that's bigger than that. And then it keeps on going.
I think it counts imaginary numbers too.
No, that fits in there.
No.
Yeah. Yeah, the set of complex numbers and the set of real numbers are the same size. That's actually not too bad of a proof. Just like you can prove that the set of positive integers is the same size as the set of positive and negative integers combined.
So Aleph sub 2 is basically human instrumentality. Nobody got that reference.
I'm sorry, I've just given you the look of no one understanding.
I'd be surprised if somebody didn't get that reference.
Okay. So, anyways, and so that's the hierarchical level difference between those. We have notions of recognizable and decidability with the Turing machine, and this is something that's particularly interesting, which is to say that a language is said to be recognizable by a Turing machine if it will accept all strings that are within that language. A language is said to be decidable by a Turing machine if it can accept all strings that are in the language and reject all strings that are not in the language. The weird thing about Turing machines is that there is a big difference between a language which is recognizable and a language which is decidable. All languages that are decidable are recognizable. However, there exist languages which are recognizable that are not decidable. And that is one of the most important proofs in computer science. Now, I want to mention that one of the things about regular expressions and context-free languages, this was not a concern we had for either of those. Because every string was either rejected or accepted by a DFA or a PDA. You could never process a string and not accept or reject it. Because eventually you would consume all of the characters. And then that would be that. Because remember, there's always those trap states you could put yourself into, which would then eat up all of the characters, and eventually either come to an end in an accept state or a reject state. So the question is, how can you have a machine which could recognize a language but not decide it? To explain that, we need to start going into details of how Turing machines actually work. Let me turn the lights on because I'm not sure how well this is showing up for the camera. Oh, that's much better. I like how lights in the new building they're nice, but they always seem to not provide as much light as I anticipate. I do miss those Moody Science spotlights that we had in that one room where we could shine them straight on the board. Highlight something. If you don't know what I'm talking about, you never will. I think I was the only professor who actually used them. And I would direct them at... Was anyone in the class when I used them?
Yeah. I think you used them in 110 on that sideboard.
Yeah. Those are nice. I'd like one of those right here. What?
Install.
Yeah. That we are no longer LEED certified because of Aaron Block. So let's talk about how Turing machines work. So let's just review quickly. So for DFAs, we have two states and we move between them by an input. Yay. For PDAs, we have the tape input. We have the word input, comma, stack input, which I'll put as a Q, stack input, and then we have stack output, which I'll put as with a Z. Okay. For Turing machines, and I'll give more space here since this is new. We have, it's not now, our input now is called the tape. So everything, the input, when you get a Turing machine, the input is the first set of characters on the tape. In that tape, you have the tape input, and that goes to the movement, which is either right or left. So in this case, I'll just have it move right. and then the output that can change that symbol. Now again, this is not necessarily destructive because you can always replace an input with itself. And unlike stacks, if you replace an input with itself, it's not like you can actually go past it again. You can always keep on going back with it. With a stack, if you replace an element on a stack with itself, you can never get to elements underneath that element until eventually you destroy it. With a Turing machine, you can replace something with itself, and then you can always just rewind back behind it.
So B is what you replace it with.
Yeah, B would be what you replace it with. Turing machines, and this is a very important part about what differentiates Turing machines from PDAs and DFAs, is that Turing machines have two states in them: Q accept and Q reject. Those will be two states that every Turing machine will have. What Q accept means is that as soon as you arrive in this state, you accept the string. Q reject says as soon as you have arrived in the string, you reject the string. This is different than PDAs and DFAs. Because with PDAs and DFAs, when did you make the decision about accept or reject?
Once you get the accept state, or once you can't get the accept state, or get there with the non-empty string.
When you ran out of input. If you were in the accept state, when you ran out of a string, you accept it. If you were in any other state and you ran out of string, you were in the reject state. Now, NFAs and PDAs have a little weirdness with epsilon transitions, but there's only really a finite number of those you can take. Again, you know it's finite because they're non-deterministic finite automata, so the number of moves that you could take there would still be finite. Here, as soon as you get those two here at the end, anyone have an idea of why you might want to have this differently? Why was that technique of waiting until we ran out of input, why would that work for a PDA, NFA, DFA, and not work for this?
Is it because the Turing machines are good?
You're close. The reason why it doesn't work is because the input comes to you on the input tape. And we can go backwards and forwards on the tape. With PDAs and DFAs, we are always marching ever forward on the input string. So eventually we would run out. With Turing machines, we can go backwards. And so you could reach the end and still not be done with the thing. And that's perfectly legitimate. You want to now have to reach the conclusion state. So as a result of this, Turing machines have three states that they're it's unfortunate they're called states, but states of being, I need another word for this. Conditioning. Someone pull up the thesaurus. What's another good word for states that's not state? Nation. You have three nations they could be in. They could be in the nation of accept, which is that as soon as you arrive in accept, you have now reached the nation of milk and honey. And you can be the nation of reject, which I guess is the House of Representatives right now. Zing, political errand.
And then the Fire Nation.
And what?
And then the
Fire Nation, yeah. The Nation 13.
Fire
yeah. Nation. So the third nation you could be in is processing. This is how some languages can be recognizable without being decidable. If you do not reject, but rather process forever, then you will not have, then that language will not be decidable. And there are languages which cannot necessarily be recognized nor it's called co-recognized, which is There are some states where you will not be able to reach accept or reject on some subset of strings. Those we don't talk about so much in this class. If you want to learn more, take theory. What? Yes. So let's draw up some examples of Turing machines so you guys can get a better idea of how they work. Okay. Can I erase this right now? So I'm going to make a simple Turing machine, and what it's going to do is it's going to accept the string AA and reject the string the string. It's going to accept any string that has at least two A's and reject any other string. Okay. So now this could also be done by a regular language, but I'm starting off with something simple so that way we don't have to worry about it. So I have my start state, which I did note the same way. I want to accept the string with two A's, so I'll start off on input A. I move right, and just for giggles, I'm going to replace it with the letter C. I don't really need to do that in this case. Then what I will do is I will see another A. I'll move right, and I'll replace it with C again. And this is Q accept. Meanwhile, if I see empty, then I have to move right, and I'll replace it with empty. If I see C, then I move right and replace it with empty. And that takes me to, actually it's called Q sub reject, but I'll just say reject, it doesn't matter. And same thing from here. If I see space, right, replace it with a space, C, right, no, it doesn't really matter at all. You can replace it with whatever. One thing to keep in mind is that notice that you keep on, even when you're heading towards the accept or the reject state, you're actually still changing the string as part of that move. That becomes an important characteristic, not with things we're going to directly handle in this class, but rather with, there'll be times where you care not so much if it's just accepted or rejected, but what is the output on the string at the conclusion of it. So if it's been accepted, what has it changed the output to be? And those are called computable functions. Those are not something we're going to have time. You don't have to even write that down if you don't want to. If you want to, you can. I'm not going to stop you. No, Rob, no! Forget. Those are very important for when we start talking about notions of reducibility. But again, that's not something we're going to cover in this class. We just don't have time to talk about it in depth. So let's process this. So one thing about Turing machines, they're infinitely long, but only in the right direction. I don't mean only in the correct direction. I mean literally to the right. You can make a Turing machine that's infinitely long in both directions, but for some reason no one does that. The style is to say infinitely long in one direction. So you might ask, what happens if you go to the left? The way that a Turing machine is supposed to handle that, it's like it's a glitching character, a glitching NPC. Just like what happens in Skyrim when you glitch, you just keep running against the wall. That's actually what happens here if you try and go infinitely off the left end of this. You just bounce and you don't even know it. So a common technique, if you know you're going to go back and forth on it, is what we did in the PDA, which is you replace the first symbol with something to denote this is the beginning. And so we'll look at a more complicated Turing machine in a bit. So let's talk about, let's go through here the input A. So the tape we would start off would be A. You typically don't even need to write more than one of those when you're talking about the input. You just write your first one because you know this can't be on your input. Then you assume that they're just that forever. So what happens here? We're in the start state. We see this. Our head is currently right there, and so that's the letter A. So what do? Well, we follow this transition, which means we move the head right, and as we're moving right, we change that character to C. Now, what happens here? Well, same thing. We move right, and we change that character to C. Yeah. Now, what happens if we were to have that? Yeah. We'll move that to the right, we'll replace it with the self and reject. Here's a question. How about that? It's going to accept. Accept, move to the right, replace that with a C. Move to the right, C, accept. How do we make this so it only accepts strings that have just two A's in a row? So just two, like just AA.
Another state with a space after the second.
Yep.
And then if it's a space, then it goes from the second.
Yep. Yep. As soon as we see the space, we know we're done. So, well, not saying we did. We not only know we're done. We know we've reached the end of the end. Now again, I've replaced it with a space here. I need not. I could replace that with any symbol I want to. So I can always extend it. If I were to do this method, and I were to see, then I guess I have to draw the line here, which is now A, right, A, C, right, C. What happens here if I see A, bracket, there, replace that with a C, see the A, replace that with a C, see that, replace it with a C. So I can keep on growing my input. I don't have to, and that's the reason why it's spaces and not just cut off after your input, because you can go into that area. And that in a lot of ways becomes your scratch pad. So if you have to do computations that require more space than your original input, you go beyond that. There is a type of Turing machine that only works, that has a tape that's just as long as its input, and it's called a linear bounded automata. It's a really, really, really important Turing machine, or subtype of, I guess, modification of Turing machine. Does anyone have an idea why? How much infinite memory do I have in my computer? Not much. I mean, really a small fraction of infinity. A linear bounded automata is essentially what can be solved on a computer. And there's a little bit of a difference between it, but it's very, very, the linear bounded automata is a theoretical model which is exceptionally close to a real computer. And so problems which can be solved by a linear bounded automata are things which can actually be solved. And so a Turing machine is what can be solved if we could have these magical supercomputers that literally, the way Alan Turing described it, was with a pencil and an eraser. We haven't fully harnessed the magical power of pencils and erasers yet. Someday we'll be there.
Really the magic sharpener, you need to keep the things sharp.
Oh, there's so many technologies we need to break through before we can really fully harness the power of a number 2 pencil. I think it's number 2. Alan Turing's work on this was largely unfinished. It could have been 2.5. We don't know. I mean, this is why we have standardized tests. We've been trying for years to fully understand what we can do with a pencil and filling in some dots. Someday. Anyways, so this is that's the Turing machine is the closest model to what we can do in general for it. And so if we can show that something can't be solved in a Turing machine, guess what? It can't be solved on a real computer. Now, we're going to reach other limitations with the Turing machine that will impact us far sooner about terms of recognizability and decidability on a linear bounded automata, that will matter far more to us. But when we talk about things which can be decided on a real computer, this idea of a linear bounded automata is something which hits very, very close to it. In a lot of ways, wow, why did I think this analogy would make it simpler? It's like parabolic geometry. It does, doesn't it? Parabolic geometry is non-Euclidean geometry where you assume that that for every dot that there doesn't exist a dot in a line, there does not exist a line which will. Basically every line will intersect with it. And the reason why it works is because it's similar to, imagine an infinitely large globe, and all lines of longitude intersect at the North and South Pole. So parabolic geometry is a simulation of geometry around the Earth, or around the globe. And so you use parabolic geometry to estimate flight paths around the planet. Gee, that analogy made it so much simpler. Linear bounded automatas are close to that. I'm just throwing out big words right now. Supercalifragilisticexpialidocious. Don't worry, even though the sound of it is something quite atrocious. If you say it loud enough, someone will think you're a professor. So, anyways, it's the last week of classes. I have to get all my stupid jokes in before the semester ends. So also when you're drinking, you'd be like, man, remember that story Aaron told us the last week of classes? Now you can record it too, so you can go back to this as reference. I want citations on me during drunken conversations about this class during the summer, by the way.
What format do you want?
What?
What format?
I'm not picky about that. Yeah, I'm not picky if it's MLA conversation, but I do want air quotes and then a citation, and they should be alphabetized too.
I'll do Chicago.
Okay, that's all right. I'm fine with that. I mean, Chicago's the funniest city in America now, so. I'm sorry, wow, I'm really distracted today. All this talk of Turing machines makes me giddy. So anyways, this is the process by which we actually move through a Turing machine. So let's do something a little bit more interesting than than just saying regular language. Let's. What I would like to do now is. I want to make a Turing machine yeah, we got time. Okay, I want to make a Turing machine that will recognize the language A to the M. Yeah, you've seen this one before. Hashtag B to the M. Hashtag A to the M. I want to point out this machine cannot be recognized by a PDA. I do not want to go through the pumping lemma, which is the process by which, the pumping lemma for context-free languages, which is the process by which you can show that a language cannot be recognized by a PDA. But instead, I'll give you an intuitive explanation for it. The reason why is to get to this, to be able to make sure that this number matches that number. And again, I'll formally spell the whole thing out. M is greater than or equal to 1. To make sure that number matches that number, you need to consume the information that you created here. I could do that with a PDA. That's parentheses matching. This is madness parentheses matching. Because what you're doing here is you're matching that number of those with those. And the process of matching that will destroy the information. So you have no idea how many A's you had. Does that make sense at a high level? I'm not giving you details about it, but Turing machines don't have this limitation because they can go back and forth. So, let's create a Turing machine that recognizes this. Guess what's going to be a test question? Oh, so much fun. So here's some things. Turing machines are, and we haven't gotten to this yet, if you can write pseudocode for something, you can create a Turing machine for it. That is it's called the Church-Turing thesis. And we're not going to go through the proof of that, but essentially, if you can write pseudocode for something, not essentially, if you can write pseudocode for something, you can create a Turing machine which will do it. So you can create a Turing machine that will create StarCraft for you. Now, time is not, it may be sucky, but you can do that. So, how do we create a Turing machine that does this? Let's talk about the pseudocode for this. What's the first thing we want to do? Well, the first thing we want to do is we want to make sure that this is in the proper order. So if someone has a string like ABA, there's no hashtags there. So if someone has a string AA hashtag BA hashtag A, that's also incorrect. So we want to make sure it's all A's, hashtag, all B's, hashtag, all A's, hashtag. Okay? So that's stage one. Guarantee order. Step two. That's where we actually need to guarantee, once we've guaranteed that it's actually in that order, then what we'll do is we'll then match for every A, make sure there's a B and a corresponding A. So we're basically taking two Turing machines and lumping them together here. Turing machine 1 makes sure it's in the proper order. Turing machine 2 will actually make sure that things work. Unfortunately, there is no process like we had for regular languages of describing how you should create a Turing machine. This makes sense, unfortunately, because it's like creating pseudocode. What's the process? If you get a problem, how do you come up with a pseudocode that represents it? Well, you think about it for a while, you drink a lot of coffee, you take a shower, you complain that you've been given this stupid fucking assignment, and you realize the answer, you write it down and realize you had a terrible mistake in there and have to start all over. It's that same process. Now, I'm giving it to you in a 2-hour test, so the questions I give you will not be that difficult. So, let's talk about how we do this first phase of making sure that we actually have in the proper order. Now, if we talk about I could write a regular expression a split machine to actually do a regular expression of this very easily to guarantee this part. Because a regular expression part, if I'm just doing step 1, kind of can't circle there apparently. That's really A to the star, hashtag, B to the star, hashtag, A to the star. That's what step 1 is guaranteeing, right? So that's basically the same mentality. I want to be using that to apply for this. There's one subtle difference that I'll have to do, aside from the mechanics of moving to the right and things like that, which I didn't have to worry about for a regular expression. And that is marking the first character when I see it. Because I have to denote the far end of the string. Okay? So, let's go and do this. So remember, it's greater than or equal to 1. I made that on purpose to make our life easier. So, we start off here, we see an A, and once we see an A, we move right, and what symbol do you want me to replace this A with? We could, but there's a convention here for denoting that it's something that, for denoting a modification of an input without destroying that. No, I'm not going to make it an empty because I'm going to come back to it later. That technique can also work too. Instead, what I'm going to do, I'll put a dot over it. So if I'm looking at this, the set of inputs that it can appear on my tape, which if you're interested in the septuple definition of this, the tape alphabet is given by gamma. Will include A, B, hashtag, cup, A dot, B dot. If you're using LaTeX, that's called cup. I don't think we'll need an A double dot. I think one dot's going to be sufficient for this. Okay? So, now what do we do? Well, now we want to make sure that we have some sequence of A's. And we're going to keep on reading A's until we get to the hashtag. So we'll have a loop here, which is on A, go right, read A. Then eventually, we'll have a hashtag, go right, replace it with a hashtag. Do I need to do my B dot here? No. I don't need to do it because I only did it there, so it denote the beginning of the string itself.
A dot is the beginning of all of your A's.
It's the beginning of the string in this case, but yeah.
Okay. But-
It'll take on another meaning in a little bit, but
So then you'll have an A dot, and then on your loop, those will all be just regular A's.
what?
The loop will all be regular A's.
Yeah. So now I have another loop here where I go B, B, I go right and replace it with a B. And eventually hashtag, go right, hashtag, and then loop here, A, right, A, and then on empty, go left and replace it with an empty. Then what we want to do, and I'll step through this in a second. We're going to run out of time before we can get through the whole thing, but we'll pick up next class with this. So the next thing I want to do is I want to rewind the tape. So on A, go right, replace with an A. On B, go right, replace it with a B. On hashtag, go right, replace it with a hashtag. And then eventually you'll see A dot. Oh, sorry, right, left. You see A dot, and then you go right and replace it with an A dot. Now I should mention, I'm not drawing this here, but if you see anything other than A out of here, go to reject. Anything other than A or hashtag from here, go to reject. Anything other than B or hashtag out of here, go to reject. A or empty, go to reject. You actually can't go to reject from here. Oh, you see B dot, go to reject. But so let's talk about A, hashtag B, hashtag A, space.
So that's supposed to be except at the very end.
No, it's actually going to be continued next class. So, we see A, we're going to start state, we replace it with A dot. We move right. Now we go through all of our A's, we soft loop, oh wait, there's only one. Hashtag. We see a hashtag, go right, transition to state. Now B, hashtag, A, space. As soon as we see space, we replace it with another space, and then go back to there. And then we see A, hashtag, B, all the time staying in the state until we get to A, and then we move forward one, and now we're currently pointing at that element. Is everyone cool with that? Cool. So next class we'll actually go through and show how to I'll build this part again, and then we'll go through and we'll finish everything.
Just like DFAs, the reject state isn't important to.
It can. It just it's going to get really cluttered to draw it, so a lot of times you will omit it. And I'll assume that if you're going down a connection, and so I'll assume when I read through your test, the couple homework problems I'm going to give you on this, that if you don't see anything, that assume that it's just reject. But it's important to know it's there. But this gets real super cluttered real fast if we put all those connections in there.